Welcome to the course Basic Weighing Terms and Weighing Influences. This course introduces you to the basic concept of weighing, common terms used in weighing, good weighing practice, and ways to eliminate adverse weighing influences. On completion of this course, you will be able to define weight and mass, state the common terms used in relation to weighing, list types of balances, state ways to eliminate adverse weighing influences. In this unit, we will look at common terms of weighing, weighing units, uncertainty of measurement, and its factors. First, let us take a look at what weight is. Weight is a force whose dimension depends on gravity. The weight of a stone on the moon is lower than the weight of the same stone on Earth. However, its mass remains the same. The display on scales indicates the weight of the object weighed in its current field of gravity, expressed in grams, that is, the apparent mass. Given that weight acceleration g varies between locations, balances must be adjusted if moved. When transported, the weights displayed by the balance changes by approximately 62 milligrams per kilogram and degree of latitude, different geographic positions. The displayed weight also changes when the balance is moved from the ground floor to elevated floors. Weight can be defined as the heaviness of an object. It is the gravity exerted on an object multiplied by its mass. The measurement unit for weight is Newton. Mass is a constant unit of the amount of matter an object possesses and stays the same no matter where the measurement is taken. It is the density of an object multiplied by its volume. The measurement unit for mass is kilogram or gram. Various weighing units are used in different parts of the world. They belong either to the metric system or to the non-metric system. For example, ton and kilogram are metric units, whereas pound, ounce, etc. are non-metric units of weight. Review the information provided on the screen to see how to convert values from non-metric to metric units. Let's take a look at some of the terms which are commonly used in weighing. Readability is the smallest unit displayed after the decimal point. It is also referred as a place or digit. Capacity is either the full weighing range, that is weighing capacity, or the upper limit of the weighing range. The weighing range extends from the lower limit to the upper limit. In general, if a balance has a capacity of 3,100 grams, then one can weigh up to 3,100 grams. Resolution refers to the smallest difference between displayed values. It can be compared to the dividing marks on a shop scale at the butcher's. Resolution is a non-technical expression for the number of scale intervals or points. For example, XP6U has 61 million points. Reproducibility is the degree of approximation between the measurement values of the same measured variable, though the individual measurements are carried out under different conditions, with regard to the measuring process, the observer, the measuring device, the measuring location, the conditions of use, and the time. Accuracy is the closeness of agreement between a test result and the accepted reference value, and combines both random and systematic effects. Whereas trueness is the closeness between the mean values obtained from a large series of test results and the true value. The true value is an accepted and recognized reference value. Trueness is expressed in terms of bias. Precision is the closeness of a series of independent measurements, and can be good even if the mean value deviates from the true value. No measurement is absolutely perfect, but is always distorted with errors. There is uncertainty associated with every measurement. Measurement uncertainty is a parameter associated with the result of a measurement that characterizes the dispersion of the values that could be reasonably attributed to the measurement. The four factors of uncertainty of weighing are sensitivity, eccentricity, repeatability, and linearity. Total uncertainty can be calculated as shown in the formula. Four factors of uncertainty: sensitivity, eccentricity, repeatability, linearity. Besides these factors related with the balance, other factors such as sample preparation, sample properties, ambient conditions, and more influence the uncertainty of measurements. Sensitivity is the change in the output variable of a measuring instrument divided by the associated change in the input variable. It is one of the most important specifications of a balance. Eccentricity indicates the scale error if the load is not placed exactly in the middle of the scale pan. Repeatability describes the ability of the scales to show the same value upon repeated weighing. It is indicated within a defined number of standard deviations. It is good if, with repeated weighings, the result is the same. Repeatability is quantified by calculating the standard deviation. To evaluate repeatability, the load and the measuring conditions must remain constant. Linearity describes the ability of the scales to represent the mass placed on it within specified tolerances at specific measurement points across the whole scale of the balances. In the previous topics, you learned about uncertainty of weighing and its balance-related factors. Now let's have a look at the consequences of measurement uncertainty. The lower the accuracy and precision of a balance are, the larger is the measurement uncertainty, red area. This means, in practical terms, a large measurement uncertainty shifts the lower limit of the usable weighing range to higher weights. It also means that the reliability of results over the entire measuring range is reduced. In this unit, you have learned that weight is a force whose dimension depends on gravity. The smallest unit displayed after the decimal point is called readability. The full weighing range is called capacity. Reproducibility is the degree of approximation between the measurement values of the same measured variable. Closeness of a measurement to the reference value is accuracy. Closeness of the mean to a recognized reference value is trueness. Measurement uncertainty is a parameter describing the reliability of a measurement. The four factors of uncertainty which depend on the balance are sensitivity, eccentricity, repeatability, linearity. In the previous unit, you learned about the common terms used in weighing, units of weight, as well as measurements uncertainty and some of its factors. In this unit, you will learn about the measurement technology, types of balances along with their resolution, calibration, and adjustment. Let us first take a look at measurement technology. The principle of the EMF cell relies on the loaded weight being compensated for by an electromagnetic force which returns the weighing system to equilibrium. The current applied is directly proportional to the loaded weight. The electromagnetic force compensation is a suitable measurement principle for electronic scales. It provides the highest performance. Now, let's learn about the four types of balances. These are microbalances or ultra-microbalances, analytical balances, precision balances, and industrial scales. Microbalance weighs 0.0001 milligram, 7 place. Analytical scales weigh 0.1 milligram and up, 4 place. Precision scales weighs from 1 milligram and up, 3 place or lower. Industrial scales weighs 1 gram and up. Delta range and dual range are the features of some special balance models designed to give users a higher resolution. Delta range is applicable over the entire weighing range. Dual range is available for the lower weighing range only. There is a hierarchy in the weights. The pyramid structure on the screen shows the hierarchy of weights. The first level on the top is the primary kilo prototype in Paris at OIML. It serves as a reference for all national kilogram pieces. In the next level are the national kilograms, which have 80 national copies worldwide. Not every country in the world has its own standards. Third level are copies for accredited and certified calibration labs. Mettler Toledo has such a lab in Greutati. In the fourth level are the weights used by service engineers and other bodies which do calibrations. There are several classes of weights available. The table lists the maximum permissible errors of the respective weight pieces. According to OIML, the class of weights is selected according to the accuracy needs of the user. According to OIML, for routine testing, the accuracy class of weights is selected such that their uncertainty is negligible in relation to the process tolerance. According to OIML, for routine testing, the uncertainty of the weight measurements of the weight pieces must not exceed 1/3 of the maximum permissible error. Calibration is determining the deviation between the measurement value and the true value of the measurement variable under specified measuring conditions. When an object is weighed, the weight displayed is called measured value. In calibration, the measured weight is compared with true value to determine deviation. As you can see on the graph, deviation increases with increase in weight. Adjustment is the process of changing the measured value to match the true value. It is an activity that follows calibration, which results in the balance display agreeing with the true value. Fact and ProFact are calibration technique features built in and available for certain product lines. Higher accuracy is one of the benefits of this calibration technique. Fact automatic calibration of sensitivity depends on the type and linearity of a balance. The calibration is triggered whenever a predetermined temperature change is exceeded. During production, internal weights are traceably connected to international measuring standards by means of primary calibration. In this process, the mass of the internal weight is determined by placing a certified weight on the balance and storing the value in the balance. ProFact is the same as fact with some additional features, such as programmable times and dates and adjustment history. Let's recap. In this unit, you learned about the EMF compensation is a suitable measurement principle for electronic scales in the highest accuracy class. 4 types of balances and its resolutions. Features of some special balance models. Delta range and dual range balances. Delta range is applicable over the entire weighing range. Dual range is available for the lower weighing range only. Features of calibration techniques. Even the most advanced weighing technology requires optimum conditions to get the best out of your weighing processes. To eliminate adverse weighing influences, there are 4 ways. These are preparing for the environment, balance preparation, reducing impact of the user, and reducing impact of the sample. You will learn more about each of these in the upcoming screens. The first way to eliminate adverse weighing influence is by preparing for the environment. This can be done by choosing a stable bench, stable location, checking the source of vibrations, setting environment, and by barometric pressure. The first thing to be done while preparing for the environment is to choose a stable bench. It is used to attain faster stability and improved accuracy. It should be solely used for balance. Place the stable bench in the corner of the room to avoid vibrations and drafts. Avoid choosing a location which has direct access areas, direct sunlight, drafts, heat sources, or are in the vicinity of magnetic or electromagnetic apparatus, heavy machinery, or traffic. Vibrations can be caused by various sources such as fume cupboard or glove box, near a production line, on 14th floor, near heavy traffic, lab benches where mixers or pumps are found, and where people work on the same bench. These vibrations can cause instability in the balance table and result in incorrect weight and long weighing time. The more stable the environment, the quicker the stabilization time. The airflow in safety cabinets leads to balance instability, but can be compensated for by the filter settings. Very stable is a low filter setting and is suitable for the lowest of vibrations. Stabilization time is very short. Very unstable is the highest filter settings for relatively high vibration environments and will result in longer stabilization times. Changes in barometric pressure result in drift due to air buoyancy influences on the weight. Compensating for changes in air buoyancy are applicable for high accuracy mass calibration and routine methods, particularly if differential weighing is carried out over long time periods and where the measured differences are minimal. That is, filter weighing. Let's take a look at the second way to eliminate adverse weighing influences, balance preparation. Standby mode allows for constant thermal equilibrium so that the balance is always ready to use. When not in use, turn off the balance using terminal on-off switch. The balance can also be put into standby mode with the help of schedulers, but avoid disconnecting it directly from the power supply. When the location of balance changes, the gravity effects on the balance need to be compensated for. Always check with external weights to avoid weighing errors. The following measures help to prevent weighing errors. Use gloves or tweezers to handle weights. Take care with weights. Choose the most suitable weights for the weighing process. Calibrate weights regularly. Keep the weights in their original box. Maintain constant storage temperature and avoid dropping weights. In order to maintain reliable and accurate weighing performance, the balance must be maintained on a straight level. The inclination of the balance should be checked regularly or immediately if it has been moved. While weighing, avoid airflow around the weighing pan to increase stability and speed of the weighing process. The smart grid is especially designed to compensate for air disturbances. The grid is made from non-magnetic stainless chrome nickel steel, and a grid with small surface enhances repeatability and reduces the risk of variation due to drafts. The large solid pan should be used only when really necessary. The automatic adjustment with internal weights helps to eliminate the risk of obtaining incorrect weighing results. Temperature change in a laboratory is the most important source of calibration error. ProFact can be programmed to adjust the balance at chosen intervals and will automatically adjust the balance according to different temperature criteria chosen by the operator. The third way to eliminate adverse weighing influence is to reduce the impact of the user. To reduce the impact of the user, calculate the value release, prepare proper working conditions, follow good working practices, handle air turbulence, use tweezers, and place samples using the tare container. Value release affects stabilization time and repeatability. Value release parameters are very reliable, reliable, reliable and fast, fast and very fast. Let's have a look at two parameters, very reliable and very fast. Very reliable parameter gives excellent repeatability of balance, but reduces the speed of weighing. The very fast parameter increases the scaling speed, but decreases repeatability. The user should always ensure that the door is locked to prevent other people from entering the weighing room. The samples are acclimated to the environment of the weighing room with regard to temperature and humidity. In addition, arrange the workbench, check the level of scales, and test scales using a control weight. The user should follow good weighing practices when weighing. Sample series should be weighed without interruption, in the same order, and by the same person. The weighing chamber should be open for as little time as possible. Always use non-magnetic material and work in a steady rhythm with the same intervals of time between weighing in and out. Lastly, clean the weighing chamber after weighing and close the doors. The user should be able to reduce air turbulences to speed up weighing. The min-weigh door prevents heat transfer from the operator's hand into the weighing chamber and also maintains a constant environment within the chamber. The movable glass shield in the XP balance inner chamber can be moved down so that air turbulences and the settling time can be reduced to a minimum. A stable reading will be reached much faster if the temperature in the weighing chamber remains constant. Always avoid transfer of body heat to the weighing vessel by holding the tare container with tweezers whilst placing it onto the balance. Always place the sample in the center of the pan, or if repeat weighings are made, then place the sample in the same position in each measuring cycle. Using tare containers will reduce errors and speed up the weighing process. The Smart Grid supports various customized tare containers which allow for direct weighing and avoid sample transfer errors. Small tare containers results in better repeatability. Additionally, the special ErgoClip baskets act like a Faraday cage, thus avoiding instability due to electrostatics. This results in more accurate measurements and a faster settling time. The fourth and last way to eliminate adverse weighing influences is to reduce the impact of the sample. If the sample is not weighed at ambient temperature, it will require more time to achieve a stable reading. Allow samples and tare containers to reach a stable temperature before weighing. The movable inner draft shield of the XP balances can be used as a shelf to hold samples until the sample temperature has stabilized. Electrostatic charging is a common phenomenon which has adverse effects on weighing. Let's take a look at the causes of electrostatic disturbances. Electrostatically charged samples will cause the balance reading to be unstable. The resulting weight will be inaccurate. Objects and substances will be more prone to becoming statically charged when the humidity is below 40%. Plastic containers and synthetic clothing are particularly problematical, as they will very quickly become charged by friction. Now let's have a look at some of the preventative measures to be taken to prevent samples and containers from becoming statically charged. Always use Hague or point deionizers. Control and increase the humidity to 40%. Use metal or porcelain vessels instead of plastic, and use ergo-clip baskets to avoid instability due to electrostatics. Magnetic objects exert mutual attraction or repulsion, which results in additional forces and results in errors in weighing. Some steps can be taken to prevent such errors. These include demagnetizing of the sample, using magnetic protection system weighing pan, increasing distance between samples and weighing pan, and weighing below balance. A hygroscopic substance absorbs moisture from the surrounding atmosphere, sometimes very quickly, causing a constant increasing drift of the recorded sample weight. Hygroscopy is difficult to compensate, but can be reduced by weighing in a special safety cabinet with an integrated special filtering system, or by capturing sample weights at a specific time to achieve better repeatability. Water or solvents placed in a container on the weighing pan will slowly evaporate, and a constant weight reading will not be reached. Some solutions for this include using a humidity trap if pipettes are being calibrated to contain the water in a high humidity environment, thus reducing evaporation to a minimum. Also, choose tear containers with narrow necks to slow down evaporation by restricting vapor loss. In this unit, you learned about the 4 results of good weighing practices and ways to eliminate adverse weighing influences. Let's recap. In this course, you learned what weight is and the difference between weight and mass, common terms used in relation to weighing, types of balances, ways to eliminate adverse weighing influences. Mettler Toledo is committed to providing customers with weighing solutions which help customers to optimize processes, maximize productivity, and feel sure about uncertainty. However, users need observing the basic rules of good weighing practice.